Hello again, and welcome to the second video on our discussion on logarithms. In this video, we will be looking at the laws of logarithms and how we apply these laws in different mathematical situations. Okay, I'm going to make this video short and focus primarily on the derivation of the laws of logarithms. After that, in the next video, we will apply the laws of logarithms in solving different types of mathematical problems. Okay, so let's begin as it is. Now, you would probably know that laws of logarithms effectively come from our laws of exponents. Okay, so if we've already gone through the laws of exponents, and we can make these laws, we can make use of these laws to derive the laws of logarithms. So first of all, which are these laws that we're going to cover? We will cover the so-called product law. We will also look at the quotient law, and we will see why they are called product and quotient laws, as well as the power law. We will look at what I tend to refer to as the unity and the null-value rules. So notice that I'm referring to them as rules, although you could think of them as laws just as well, right? We will see how we come up with the so-called the change of base rule. And finally, we will look at the function and inverse function law. Now, the function inverse function law, we will not derive this one. Instead, we will make use of the other laws to show that that last law there holds true, okay? Because the derivation requires us to have done some functions and therefore to reason from that direction. And since we haven't done that yet at this stage, we will merely show that those rules hold true by making use of the product and the quotient rule and so on. Okay, so without wasting additional time, let's begin. Let's start by going back into what we already know, and that is the laws of exponents. So if you remember correctly, if you remember what we've done before, before going to logarithms, we first start with exponents. And one of the things we did was to look at the laws of exponents, right? And what are the laws of exponents then? Well, the first law of exponent is actually the product rule. And it says that if similar bases are multiplied, so base A and base A are being multiplied, then the result will be the same base but with the exponents added together, right? So the product of A power m and A power n is A to the power of m plus n. The quotient rule for exponents comes from the fact that we are dividing A power m and A power n. And it says that if we divide A power m and A power n, then we will get A to the power of m minus n. So this we know because we actually proved it. We showed it very, very easily. The third law, which is also the power law, is that the power of A power m is just A power m multiplied by k there. All right? So that's law number 3. And law number 4 is that A to the power of 1, any number to the power of 1 is always equal to that number. And going with that law is also that any number to the power of 0 is always equal to 1. Of course, we had to prove that this is true, that A power 0 is always equal to 1. Law number 6 from exponent, not exactly a law, but this really emanates from the above laws. Primarily law number 2, that A to the power of negative n is the same as the reciprocal of A power n and vice versa. So A power n is also A power m is the equivalent of the reciprocal of A to the power of negative m, which is to say that we can move this to the denominator, but if we do so, the exponent, the sign of the exponent changes. Okay? And number 8, finally, we showed that A to the power of a rational power, m over n, is the same as the nth root of A power m, or the nth root of A, everything to the power of m. All right, so this is called the rational power rule. Okay, so keeping these rules in mind, we are going to make use of these same ideas to come up with the laws of exponents. All right, so let's begin then. From exponents to logarithms, we already know that, which we did in part 1 of the topic on logarithms, we saw that any number n can be expressed as an exponent. That means n can be expressed as a to the power of k, or we can express it in logarithmic form as log to base a of n. So n is the number, a is the base, and k is the exponent. An example of this would be 1000, or let's say 100, is the same thing as 10 to the power of 2, and 1000 is the same as 10 to the power of 3, okay? And so keeping this in mind, it means I can express this 2 is the log of 100 when the base is 10, and 3 is the log of 1000 when the base is 10, like that. So we've done this kind of thing, and we're going to rely on our understanding of this to come up with the laws of logarithms. Okay, so keeping this in mind then, if given 25 is the same as 5 to the power of 2, so that can be expressed as 2 is the log to base 5 of 25. We know how to do that already. We know that 64 is 2 to the power of 6, and therefore we can change that to logarithmic form and say 6 is the log to base 2 of 64. We know that if p is 10 to the power of x, then we can express x as log to base 10 of p. Okay, and finally, if y is e power n, then we can express n as log to base e of y. And we will see later that log to base e can be expressed merely as ln instead of having to write log to base e of y, like that. Okay, so let's start by looking at the laws of logarithms, and we are saying that the laws of logarithms arise from the laws of exponents. So if you remember those laws of exponent, and you also remember what we learned in the first part, which was converting from exponent or index notation to logarithmic notation, then we can start with that here. All right, so what do we know already? Let's express two numbers a and b. For example, what I just said, we expressed 100 as 10 power 2 and 1000 as 10 to the power of 3. So let two numbers such as 100 and 1000 be expressed in exponential notation, so that a is as lowercase a power m and b is lowercase a power n. Let's call that set 1. As an example, one more time, let's think of this as 1000. So 1000 being 10 to the power of 3 and 100 being 10 to the power of 2. So think like that. So we have two numbers a and b, and we are expressing them in exponent notation like that. So think about that, and now we can move on. If we change those numbers from exponent notation to logarithmic notation, then clearly this is going to be m is the log of a to base small letter a, and n is going to be the log of b to the base lowercase a, like this. All right, so m is log of a to the base lowercase a, and n is log of b to the base lowercase a, like that. Keep that in mind. Now, with that in mind, we can reason that if I take m and add n there, that is equivalent to taking log of a and adding log of b, like that. All right, so we are adding log of a, so m plus n must be log of a plus log of b based on what we've written there. Okay, I'm going to move that so that we see it more clearly. So m plus n must be log of a plus log of b. But similarly, m minus n, since m is log of a and n is log of b, then m minus n must also be log of a minus log of b, like that. Okay, so that is true. The second thing we want to do is to use our knowledge of the laws of exponent. If I multiply a and b, that is equivalent to multiplying a power m there by a power n, like this. By the laws of exponents, a times b must be a power m plus n. Why is that? Because, I can go back a little, I'll put that there and go back a little, because a, if I take a and I multiply by b, that is equivalent to taking a power m and multiplying by a power n, and by laws of exponents we know that that is a power m plus n, like that. So I know that a times b is going to be a power m plus n. Okay? Similarly, I also know that a over b is going to be the same as a power m over a power n, which in turn is going to be a power m minus n. So this is from our knowledge of the laws of exponent. Right, and therefore we can express that neatly as a times b is going to be the lowercase a, the base a, to the power of m plus n. And same way, we can see that a divided by b is going to be a to the power m minus n, like that. And if we do the same thing that we did to these ones, that is, to change this from exponent notation to logarithmic notation, now you notice the power is not just n or m as before. Now we have a power of m plus n. So we keep that together. So we can say m plus n there must be the logarithm of this product here, just like m was the logarithm of a to the base lowercase a. M plus n must be the logarithm of this product AB when the base is a, like this. It should be possible to write, if we consider this as the second set, we can now say m plus n must be equal to the log of a times b. And similarly, m minus n must be the log of a divided by b, like that, under the same base. Okay, hopefully this is very clear. Now, the next thing I want us to look at, now we keep track of this result here and that result there. So I'm going to keep them all together and remove everything else. Let's see what happens. So what we have then is, the first case is this, that m plus n is log of a plus log of b, which is what I've written there. The next thing the result we've come up with is m minus n must be the log of a minus the log of b, which is there. Okay. The next thing that we have is these lower ones here. I'm just going to pick these ones. We've also seen that m plus n is log of a times b under base a. Okay. And lastly, that m minus n can be expressed as log to base a of a divided by b, like that. So keeping that in mind, I think I can now remove this and then we deal with that. All right. So now we can talk about the quotient and the product rule. You should already be able to see them from the results we found. That if I take the result 1 and result number 3, you can see there that this is m plus n and this is also m plus n. So these two must be equal. Okay. So reasoning from 1 and 3, we can see that log to base a plus log to base b must be equal to the third one there, which is log of a times b, like that. And this is what we refer to as the product law, or the product rule for logarithm. So this is the first law of logarithm, referred to as the product law. And why do we call it the product law? Because the result of a product there is the sum of the individual numbers. So the log of a product of numbers is the sum of the individual logs of the numbers themselves, like that. Okay, this law can be confusing. You will find some students now multiplying, putting a multiplication sign here and putting an addition sign there. Please be careful that you don't lose track of how we came up with this rule. All right, but by solving several questions, numerous different questions, hopefully you will master this law. Okay. Secondly, by looking at our result 2 and result 4, you can see m minus n there. This must be the same as that. And so we can write by looking at 2 and 4, yeah, that the log of A minus log of B must be equal to the log of A over B, okay, like that. And this is what we refer to as the quotient law of logarithms. I hope this is clear. Let me know if this is not making sense, and we can find a way to explain it for you. All right, so what we've done now, we've derived the first two laws of logarithms. There's one other very special one, and then we will see how the others come up. The others will be relatively easy to see. Okay, let's move on then. The next is the so-called power law. So those two are the product and the quotient laws. And now we go to the power law. Okay? The power law arises from the product law. So which is the product law? The product law says, that log of A plus log of B is the same as log of A times B, right? So that's the first one. There is the product law. The second one is the quotient law. But the power law comes very quickly from as a result of that product law. Let's start with the product law. Now, instead of having A and B there, let's say that B is also equal to A. So we can see that log of A plus log of B must be log of A times A there, if that is also A. Okay? Based on that law, log of A plus log of A, obviously this is 2 of log of A's. So this is obvious. There are 2 of them. So we can say this is 2 log of A. Okay, on the left-hand side. But on the right-hand side, using that law there, we can express this as log of A into A, using law number 1 there. Okay, so if we use the first law there, then we end up with log of A times A, which is in fact the same thing as log to base A of A squared. Okay, so we can remove A times A and put A squared instead, which is to say that twice log of A is the same as log of A power 2, like that, right? Very, very easy to understand. In the same way, we can think of log of, if we had 3 of them, then 3 log of A is the same thing as log of A, right? Plus log of A plus log of A, like that, which is the same as, according to law number 1 there, law of product rule, which is the same as A times A times A, A times A times A, based on that rule there. And so we can express this as log to base A of A power 3. So clearly, just like before, 3 log of A must be the same as log of A power 3. It's almost like we are allowed to pick this from here and just bring it to the top there. Okay? In the same way, if I had, now I'm going to generalize. So if I had n, suppose I had n log of A. I'm going to leave out the base. We can put any base you like. Then this must be the same as log of A plus log of A plus, and as many as they are, plus log of A, which is to say this is the first A, this is the second, and they go on until I have the nth log. So I must add n of them, just in the same way that if this is 3, then I must add 3 of them. If that is 2, then I must add 2 of them. So if there are n log of a's, then I must add n of them, which is to say that here I can combine all of them using our first law there, and I will have log of A times, and all of them until I am there. There should be n of them, which I can therefore write as log of A to the power of n. Okay? So we can conclude already by just looking at the pattern. Okay? So by just looking at the pattern we have, we can see that n log A is the same as log of A power n. Okay? So by conclusion then, we can say that n log A is the same as log of A to the power of n. If n is on the side and you need to, you can always move it so that it becomes A to the power of n, like that. This law happens to be very, very powerful in that we can extend it so that n does not have to be just integer. So n could be a fraction as well. So if n was a half, then I can write this as a power a half, which also happens to be the square root of a, like that. So n can be any number, including irrational numbers. It can be pi, it can be e, it can be practically any number that you can think of. It can also be a complex number. Okay? We will see how to use this law together with the others in solving problems related to logarithms. And therefore, we can now include another law there, which is called the power law. We can add it to the group of laws that we already have. Okay? Now, these are really the most, this is as difficult as it comes because the others just come by themselves, come very easily. Let's see what goes on then. So that was the power law. The next is the unity and the null value laws. What does that mean? Now, we know from laws of exponents that a to the power of 1 is a, and also that a to the power of 0 is 1. All we need to do here is to express this in logarithmic notation. Change from exponential notation to logarithmic notation. We see that 1 is the logarithm of a to base a, okay? And 0 is the logarithm of 1 when the base is a. In other words, log to base a of a. So from this one here, okay, 1 is the log. 1 is the log of the number opposite. So 1 is the log of a when the base is a. So 1 is the log of a when the base is a. So we've changed that to logarithmic notation. This has a consequence. It means any number to the same base is always equal to 1. So 5 to log of 5 to base 5 is 1. Log of 2 to base 2 is 1. Log of 100 to the base of 100 is 1, and so on. Log of x to the base x is always 1. And from here we can see that 0 is always the logarithm of 1 to any base, like this, which is to say the log to any base of 1 is always 0. So log to base 10 of 1 is 0. The log of 1 is 0 under any base. Okay? So here are examples. We are saying, so this will form our, so this we refer to as the unity law, and that is called the null value law, or rule if you like. So in addition to the 3 that we worked out earlier, we can quickly add in these ones. These rules become very useful when we are simplifying logarithms, as you will see when we get there. Okay? There are some of the laws you want to keep intact in your mind at any time because they will always tend to appear when you are simplifying a very heavy, a very long or large string of logarithm terms. Okay? When you're combining them or when you're splitting them, these two tend to appear easily, and when they appear, if you end up with log to base 2 of 2, you can always reduce it to 1. So it makes calculation or simplification very, very easy. Okay? So here are examples of what I'm saying then. So log to base 10 of 10 is 1. Log to the base of 2 is 1. Log to base 5 of 5 is 1. Log to any base of itself is always 1. And secondly, or similarly, the log of 1 is always 0 irrespective of what base it is. So log to base 2 of 1 is 0. Log to base 10 of 1 is always 0. And all this is true because of that statement, which we all know to be true. Okay? Log to base 4.7 or log to base pi or log to base e of 1. Log of 1 is 0 under any base. Okay, so that's that law there. Next, we look at the change of base rule or law. This is about sometimes it's going to be necessary for us to change from a given base to another in the process of simplifying an expression. And we will see examples after we have completed these laws. All right, here is an example. Suppose that some logarithm, I'm going to call it L, is expressed like that. So L is log to base a of b. then we can change this to exponential notation. So we are going to change the base. That means that right now the base is a. We're going to make it another base. So we can pick any other base we want, base 2, base 10, base 5. Okay, so we'll just use a different letter to imply that we are changing the base. So the first thing we do is to change the logarithmic notation here into exponential notation. If we change it to exponential notation, then we can write that b is the same as a to the power of l. So a to the power of l must be equal to b. We have changed it into exponential form or exponential notation. Once we've done that, we can now take the logarithm to any other base we feel like. So let's take the law to say base m or base k, whatever you choose. I'm going to take log to base m of both sides. That means I'll take, if I take saying taking log to base m means you do it on both sides, right? Whatever you do on the left, we do on the right hand side as well. So if we take the log to base m of both sides, then I have log to base m of b must be equal to log to base m of a power l. And now I can make use of my law number 3 there, which was the power law, to just move this l from here to the side, because we can easily move it from the side of log there to the top, or from there to the other, okay, since the two are the same. So using the power law, then we will have log to base m of b must be equal to l multiplied by log to base m of a, and that is due to the power law that we already know. Okay, all I have to do now is to make l the subject of the formula, and to do that I divide both sides by log to base m of a. If I do that, divide both sides by log to base m of a, I'm going to remain with l there, and on the other side I'll have log to base m of b over log to base m of a. I'm going to write it the other way around. So I end up with l being equal to log to base m of b divided by log to base m of a. I hope this is making sense like that. Please check and be sure you see how that comes about. Now, so we are saying then that l can be expressed as log to base m of b over log to base m of a. But guess where we began? We began by saying let l be log to base a of b. So we are effectively saying that this is the same as that. So l is log to base a of b, but it is also log to base m of b over log to base m of a. Okay, what is this turning out to be? Let me put that there now. I move that slightly and slot in log to base a of a, and that is called the change of base rule. Okay, let's see. What are we saying? If I'm given log to base b, log to base a of a number b, then I can change this to any other base I feel like. Okay, all I have to do is take a new log here. So I'm going to put a new log right there. So I can say this must be equal to, and I take the log of b and divide by the log of a to whatever base I feel like. So I'll take log of b and I will divide that by log of its base, which was a. Okay, this was the base of this. So I'll take log of b, divide by log of a, and I can choose whatever base I like. I can say base k. I can, if I put base k there, then it's base k at the bottom. So I've changed everything to base k, right? K could be anything, can be a 2, can be a 3, whatever you like. You have changed the base of the original log. Okay, this is going to be also very useful in solving logarithmic equations or in simplifying logarithmic expressions. Okay, this brings us to the end of the laws that we actually need to derive. So we already have this, and now we have a new law there which we can add into the system. So these are the laws of exponents that we use to solve logarithmic or problems relating to logarithmic and even exponential equations, expressions, and so on, functions as well. But in addition to this, there is another law which we will not derive now. As I said, we cannot derive it now because of the fact that we have not gone into the ideas of functions and inverse functions, and for that reason I will put it here without actually deriving it. But of course we can use these laws to show that this last law here also holds true, and that is that the log to base a of a power x is actually equal to x. This is easy to see directly from law number 3 there. So from law number 3 here, we can already see why this is true, because from law number 3 we can interchange this power, we can put it right there next to it. So if I'm given log to base a of a power x, then I can write that as x log to base a of a. But again, we saw from this law here, from law number 4, basically the unity law, that log to base a of a is 1. So this thing here is effectively 1, and so this leaves me with x, right? And therefore, this first part of the law is obvious. It's pretty clear to see, easy to see. To show that the second part is also true, we can simply take the log of both sides. I'm going to use a different color. Okay, to show that a to the power of log to base a of x is the same as x, we just need to take log to base a of both sides. So if I'm given, let's say here, a, that doesn't look very neat. So if I have a to the power of log to base a of x, and let's say it is equal to x, if I take log to base a of both sides, I can take log, I will use a different color, I can take log to base a of that side, and if I do that, then I also have to take the log to base a of this side. So I will remove that and put log to base a, and I can put my x here like that, right? So if I take log to base a of this side, then I take log to base a of that side. Remember, we are looking at this problem here. Hopefully you can see it, that one there. So I've taken log to base a of both sides. Now using law number 3 here, I can move, this is the power of this thing here. This is the power of, this is the power of a, so I can move it to the side. And I end up with log to base a of x. Okay, the power moves to the side, and now I have times log to base a of a must be equal to log to base a of x. Now is this true? Well, log to base a of a from here, log to base a of a is 1, so this thing here is actually 1, and we can see the left hand side is the same as the right hand side. So in that way we have shown that these two expressions are the same. But the reason why we refer to them as the function and inverse function rules, that will come once we have understood what functions and inverse functions are. This brings us to the end of this video. Let's just consolidate at what we've done, after which we will go into the next video and solve some real examples of the application of these laws, right? So in consolidation, what is it that we have covered today? We can see that the first thing we did, we made use of the laws of exponents to derive the laws of logarithms. That's really what we've done here. One, we found that the first law there, log of a plus log of b, provided the base is the same, is the log of the product of a and b, and because of that end product there, the reason why we refer to this as the product law. Okay, similarly, we found the second law there, which was that log of a minus log of b is the same as log of a divided by b. This is base a just like this, okay? So be sure to ensure that the bases are the same. So this is base a here, okay? And this is also base a, if we add the two logs, the result is the product, A and B, like that. So the second one there is called the quotient law. Law number 3, we found that n log of A is the same as log of A to the power of n. So again, just keep the bases the same, all right? As long as you ensure that you are working under the same base, this is true. If the base is not the same, then that cannot be true. All right. Number 4, we saw that. So this is what we refer to as the power law. And number 4, we also saw that log to base A of A is 1, and log to base A of A is 1, and log to base A of 1 is always equal to 0, where A can take any value that is not that is positive. Okay, right, and that is the unity and the null value rules. Next, we also saw how to change the base. So given log to base A of B, we can express log to base A of B as log of B over log of A. So log of B to base A can be expressed as log of B over log of A under a new base. You can choose that base as you please. Now, the way we choose the base, of course, in a calculation, when you're given a problem, the base that you actually choose will depend on the terms that you're given in that calculation. So you always try to change the base so that it is the same as the bases in the other terms that are available in the expression. All right, this is called the change of base rule. And finally, we have the function inverse function rule, which we have not derived, but that we have proved is also true. Okay, next we will, in the next video, we will be seeing how to apply these laws in solving questions that you meet regularly in your mathematics encounter. All right, this brings us to the end of this video. If you're seeing this for the first time, please consider subscribing and sharing this video widely with those who might also find it useful. All right, thank you very much. I'll see you in the next.